Hello everyone, welcome to the second video of chapter 1 for the Material Science MEC 300. As we discussed in the previous video, this is like introduction to the Material Science class, and we already introduced these different learning objectives, and we discussed the difference between material science, materials engineering. This is over the previous video. Also, we discussed the different disciplines of material science like material processing, material structure, properties, performance. Even we distinguish between the different types and different levels or forms of the material structure. Through this video, we're gonna continue this and finish this chapter, starting with the classification of the material, but based on their chemical makeup or based on chemistry. So we're gonna start with the classification, but something that I'd like to mention here about the classification of the material, there are different approaches and different ways based on which we can do classification of materials. We can do the classification based on their chemical composition into metals, ceramics, polymers, or based on their application side. So we're gonna say that this is like engineering classification of the material. We can do even the classification based on their properties. We can do the classification based on their microstructure, based on their structure. So there are, what I mean that there are different approaches, different ways of classifying materials that we are using as engineers. But here we're gonna discuss the classification first based on their chemistry, then we're gonna do the classification but based on their structures. So starting with the classification, materials can be classified based on their chemical makeup or based on their chemical composition into metals, ceramics, and polymers. And you could say that these three types of metal, these are the natural material that we can derive from nature. But in addition to this material, we could involve a fourth type of material, which is known as a composite material. But this composite material is man-made material. This is the material that we can produce, but it is not a natural material. The natural material, it would be either metallic, ceramic, or polymer. So these are the three types. But before we go deeply through what does it mean, metals, ceramics, and polymers, let us demonstrate some keywords here, starting with the element. What does it mean, element? Element is a substance. So element, and you should have an idea about the thing from the physics even class, especially the chemistry engineers. Element is a substance that cannot be broken down into any other substance. Substance here, it means that it is like a material. Something that you can touch. We said that in the previous video that the material is something that we can touch by hand, right? So any substance, it is like any material. The element, it is like a small material, but it cannot be broken down into any other thing. It is like a pure form of the material that is consists of one single thing. This thing is element. Every element is made up of its own atoms. So the element, it would be the element actually, it is like set of molecules or set of atoms. Lots of atoms formed together to form one single element of a material. This element could be considered like a pure material example. Pure thing that is composed of only one single atom, but there is no any other atom, right? So if there is another atom that is somehow embedded inside all of the atoms of the element, this won't gonna be counted as element, it will be counted as a compound, chemical compound. This is from the chemical point of view. So this is why the chemical elements are all very different from each other. It means that in terms of chemistry, the element is a unique thing, cannot be broken down. It is just one form of set of atoms that represent an element. So that's why we have the periodic table of elements. So these elements, actually, these elements are not necessary to be materials. You got my point? So these elements, in terms of material concept, they are kind of pure material. This is the ideal form of the material. Every one of these elements represents a pure or the ideal form of a pure metal, non-metal, ceramic, polymer, pure form of the material. Make sense? So in terms of chemistry, these are, or in terms of physics, we used to call them as elements. But in terms of material science, a material, it would be composed of multiple elements. So everything in the universe, everything in the universe that we can touch, it would be considered in a form of a material, contains the atoms of at least one or more elements. Like if we're gonna consider a material that is composed of one type of atom, it means that this material, it is like an element, which is a pure. So we're gonna say that this is a pure material that consists of only one single atom, not just one single atom, no, one type of atom, like one atom, and this one single atom is repeated so many to form a material or to form an element. So we could say that the element is like a pure material. But generally speaking, most of the materials that we are using or we are experiencing, even the material that we derive from nature, they are coming up with multiple elements, with multiple atoms. Not just one element form a material, no, multiple elements form a material. Multiple things of these elements that form the periodic table, we mixing them together, we end up with one single material. Make sense? So the material, it could be from one single element or multiple elements. So the element, it is like kind of pure material. Make sense? Which rarely happen in nature. Why? Because most of natural materials, they are mixture of multiple elements together. The periodic table lists all the known elements and group them together according to their similar properties as already given in the periodic table. I won't gonna go deeply through the periodic table because this is not the main concern of or objective of this course. But the thing that I'd like to demonstrate, and that's why I'm bringing this table here, is that we can do the classification based on of these different elements into two groups. One group is metallic elements. Remember, here we are talking about elements, not materials. You got my point? Like you may have a metallic material that is composed of multiple different forms of elements. You got it? So the elements within this table can be grouped into two types, either metallic or non-metallic, or metals or non-metals. So metals, like all these elements with this color, like the orange, the yellow, this kind of orange, the purple, all of these elements that with this color, so this can be classified aluminum, zinc, all of these elements are metals, nickel, cobalt, Fe, which is iron. All of these are different forms and different types of metal elements, not metal materials, remember. But definitely they're gonna form metal material or any other material, as I'm going to explain. But the key idea that these are elements, not just material, right? Just deal with them like they are elements. So all of these elements with this color that belong to this list of colors, they are classified as metals, but the other elements are known as non-metals. Make sense? So again, the element, this is the smallest thing, substance that cannot be broken down. This is like pure material, and it is comprised or consisting of only one single type of atom. And as I mentioned, most of the material that we are experiencing or found in the universe, they are not just consisting of one single atom, no, and instead they are containing multiple atoms mixed together to provide or to form a material. So then we can do the classification, and this is how we are going to distinguish between metals, ceramics, and polymers. For example, metals. Let us start with the metals. Materials in this group contain one or more metallic elements. So the main composition of any metal material is that it should contain metallic elements. What are the metallic elements? This element that belong to this group. Any one of these elements form a metallic material. But the key condition is that the percent of the metallic element that form this material, it should be high, like 90%, 99%, 95% or above. In that case, we're gonna say that this is a metallic material. So the metallic material it consists of one single element or more than one element, but the key condition is that this element, it should be metallic element. Like for example, if we're gonna have the material, it is just copper. So it is a metallic material. But if the material, it is 100% copper, so we're gonna say that this is pure material. We could even mix copper with aluminum, which both are metals. So we're gonna say that we do have a metallic material, but made of two different elements, two different metallic elements. Make sense? Something that you should understand about metals, and it's gonna be very clear as we move on through this course, is that metals, in many of the cases, we are using them in the form of alloy. Alloy is something that it is not pure metal. So the pure metal by itself, it is very weak in terms of mechanical properties. It is not preferred in terms of application, in terms of chemical applications even. It means that the most of the engineering use of metals requires using metals in the form of alloy. So the alloy metals usually are used in the form of alloy, and alloy is a chemical composition. The condition that there should be a chemical reaction happens here. It is a chemical composition of one or more metallic element and one or more non-metallic elements. So again, the alloy, it is a chemical composition of metal plus non-metal element. So for example, if you mix aluminum with the oxygen, which is non-metal, so metal with non-metal, you're gonna end up with an alloy. But the key condition is that the highest percent, it should be for the metallic element. Like the aluminum, it should be with 99% aluminum, and you're gonna have 1% of oxygen, for example, or any other element. So this other very small fraction or very small percent of the non-metal makes a material which is a still metallic material, but in the form of an alloy. So it is known as metallic alloy. The metallic alloy, it is very preferred in terms of properties over the pure metal. That's why in most of the engineering application we are using alloys. And it's gonna be clear, and we're gonna explain how we are going to do this alloying thing and how the properties is going to change up on alloying the metal in comparison to the pure metal. In metal, the fraction of the non-metallic part is relatively small. This is the key condition, that the highest percentage should be for sure for the metallic part. Examples of metallic element that would be used for making metals: iron, which is the Fe, aluminum, copper, titanium, gold, nickel. Examples of non-metals like carbon, nitrogen, oxygen. Examples of metal alloy, which is a mixture between metal plus non-metal, is steel. Steel, it is iron plus carbon. It is not just iron. Iron, the pure iron, it is very weak. But all the engineering application, in terms of civil engineering application, mechanical machines, everything that we are using steel, not iron. The iron is very weak. Steel is very strong in comparison to the pure iron. So if the pure iron, for example, steel, the percent of carbon in the steel, it would be like 1% carbon steel, carbon. And plus the iron, the rest is like you're gonna have like 99% Fe and plus 1% of carbon. This 1% of carbon significantly enhance the properties of the pure iron, make it steel, which is like different material, stronger material. Make sense? So the steel, and the difference between the steel and the iron, this is like kind of classification that based on the properties or based on the engineering concept, like how you are going to use this material. Fe by itself as pure, it is relatively weak. But if we added carbon, we're gonna end up with the steel. Steel, it is another type of material based on the engineering concept that provide more enhanced properties that would be used for more application than the pure iron. So this is the engineering classification. This could be considered, the difference between Fe and steel would be considered in terms of engineering concept, in terms of engineering classification. But in terms of material science, both are steel, both are metals. Fe is metal, steel is metal, is metallic material. Both are metallic materials, but the difference is that this is metal, but this is metallic alloy with more enhanced properties because of the addition of the carbon. The same thing applies to the stainless steel, that if we add it to the Fe with the highest percent, a small percent of chromium or nickel, you're gonna end up with a stainless steel that can withstand the stain and of the steel, and this is one of the very important types of metal that would be used for many applications for sure, right? So this is very quick. What does it mean, metal? Again, you should distinguish between an element and material. An element is just a chemical element that is single substance that is composed of atoms. If you added multiple elements together, you're gonna form a material. So the material is a composition of one type or different types of elements. Metals, for sure, they should contain at least one metallic element with the highest fraction. Plus, we can add other non-metals. If we did so, we're gonna end up with an alloy. The alloy, it is a chemical reaction. There should be a chemical composition or a chemical reaction between the metal and non-metallic element. It means that upon this chemical reaction, we cannot decompose again these two elements, or we cannot remove the carbon from the iron anymore. They're gonna be mixed together to end up with FeC, which won't gonna be broken down anymore into Fe and carbon again. Make sense? So this is the first type. Ceramics are compounds. They are chemical compounds between metallic and non-metallic elements. So somebody would say, okay, hold on. We do have here metals plus non-metals again. In metallic alloys, we do have metals and non-metal elements. So can we consider metallic alloys or metal alloys ceramic materials? No. The key difference between the ceramic and the metal alloys is both are composed of metal plus non-metal elements. Here we do have metal plus non-metal elements, right? But the key idea is that the percent of the non-metal, it is very high or very close to, or in some cases it would exceed the percent of the metallic element. But here in the metal alloy, the fraction or the percent of the non-metal element, it is very small, as 1%, 0.05%, in that much. Very small amount of non-metal. This is going to enhance, like you adding some salt over your food or a plate of food, right? So it is just adding a very tiny thing that it would enhance the properties of this pure metal. Pure metal is very weak. If we added this very small amount of non-metal, we are going to enhance the properties. This is the concept of alloying or metal alloys. But ceramic, that the material is composed of metal plus non-metal, and the percent of the non-metal here, it is very high, that form another form or provide another form of the material, or another group of material as ceramics. So ceramics are chemical compounds of metal plus non-metal elements. They are most frequently, these non-metal things will be either oxides, nitrides, or carbides. Examples of ceramic materials are aluminum oxides, or alumina, which is Al2O3, silicon dioxide, which is commonly known as silica, SiO2, which is silicon plus oxygen, metal plus non-metal element. Silicon carbide, which is silicon plus carbide, which is like carbon, which is just silicon, which is metal and non-metal. Silicon nitride, glass, cement, all of these are different forms and different types of ceramics. They are mainly chemical compounds of metal plus non-metals, but the fraction of the non-metal is kind of high, so that's why they cannot be considered as metal alloys. Polymers are organic compounds, chemical compounds as well, that are chemically based on carbon, mainly depend on carbon, hydrogen, and other non-metal elements. So their main composition are non-metallic materials. Their main composition is non-metallic material, especially carbon and hydrogen. They depend a lot on the carbon and the hydrogen in their MER. This is the main building unit. And poly, so the word polymers, it means multiple. MER, this is like the unit cell. This is the main unit. Like you do have one MER and another MER, so you're gonna end up with polymers. You got my point? So this is the breakdown of the word polymer. What does it mean? Polymers include familiar plastic and rubber, so all rubbery material which are very flexible material, all the different types and forms of plastics, these are classified as polymers. Examples of polymers are polyethylene, nylon, silicone rubber, PVC, and polystyrene. All of these polycarbonate, all of these different forms are different types of polymers which used in different applications. So what we did here, we just discussed the classification and the different types of materials based on their chemical composition. So metals are pure metals, are composed of one or more metallic elements. We may add non-metals, but with very small fraction to enhance their properties in the form, or this is gonna provide metal alloy. There is no alloys in ceramic. There is no alloys in polymers. Alloys only for metals. You got it? Ceramics, they are chemical compounds of metal plus non-metals with very high fraction, with a high fraction of the non-metal to be ceramic, and mainly depend on oxides, nitrides, and carbides. Polymers are organic chemical compounds that depend mainly on non-metals, especially carbon and hydrogen. And these are examples of the plastic and rubber material, and they do have their own properties as a group, as a special group. So these three types of material are natural material. What does it mean? It means that these are the material that we can derive from nature. We can derive them from nature. We basically, or we can derive them by mixing these elements that found in the table, right? But composite material, it is like kind of man-made material or kind of engineering material. This is the engineering concept. Now we can engineer something. If you remember our definition to the materials engineering, that we are going to mix or design the material structure to provide certain properties, right? To produce a new, not a new material, to produce a material with a certain properties based on our understanding of material science. This, or based on the naturally developed material like metal, ceramic, and polymer, this is gonna give us the composite material. So simply, composite material, it is a mixture. It is not a chemical compound. For example, ceramics are chemical compound. Alloys are chemical compound. It means that there should be chemical reaction between metal and non-metal, or between two metal elements, whatever it is. The same thing for polymers. But composites, there is no chemical reaction. Composites, it is a mixture. Mixture, it means that there is no chemical reaction. It's just mixing two elements together. Make sense? For example, a composite is a material made from two or more constituent materials with significantly different chemical properties. Like the key idea that these two materials, they should be different in terms of chemistry. Like you mix metal with their own chemical properties with ceramic. So you're gonna end up with metal ceramic composite. You're gonna mix some metal with some ceramic material, two different material, chemically different material. You're gonna end up with a new material, which is composite material. This composite material, metal ceramic material, it is not found in nature. We are making this material. These are man-made materials. We manufacture them. The same thing, we can mix metal with polymer. So we're gonna end up with polymer, with metal polymer composite. We can mix polymer with ceramic. So we're gonna end up with ceramic polymer composite. So all of these are different. We can mix three even. We can mix polymer with metal with ceramic to end up with a composite material. We can embed even different forms and different, so we can end up with a hybrid composite. So composite, simply the concept of a composite material is just to mix different materials together to end up with a new material. But this mixture, it shouldn't involve any chemical reaction. There is no chemical reaction to end up with a composite material. So it is a mixture of two or more constituent material with significantly different chemical properties. When these materials are combined together, a composite is produced with characteristics and properties different from the individual constituent material. That the new developed material, the new composite material, its properties is different than the metal, different than the ceramic. But what is the key idea behind the composite material? Why we are making this composite material? Any one of the three groups that we discussed, metal, ceramics, and polymer, they do have their own good properties and bad properties. They do have their advantage and disadvantage. So what we are trying to do by the composite material is to try to bring the good thing of metal with the good thing of ceramic to end up with a perfect material, kind of. The same thing, the good thing of metals with the good thing of polymers to end up with a perfect material. So this is man-made material that should be produced with properties better than their constituents, better than the pure metal, better than the pure ceramic, better than the pure polymer material. In composite, there is no chemical reaction, as I mentioned, between the material constituent. The constituents are arranged to share loads together. They are arranged together and they are separate. Inside the material microstructure, you can even distinguish the metal from the ceramic, the metal from the polymer. When you're gonna look to the material microstructure, this is the key idea of the composite material. So what distinguish, or what is the essential difference between a composite material and an alloy? The alloy, there should be a chemical reaction. You're gonna mix metal element with non-metal through a chemical reaction to end up with an alloy. The alloy, it gives properties over the pure metal, which is better. The same concept for the composite material. It enhances the material properties. It provides more good properties, but without chemical reaction. By mixing different material types together to end up with a composite material. Make sense? So these are the different types and the classification of the material. And as you can see, this classification mainly depends on their chemical composition. Metal are composed of metal, non-metal. Ceramic, it is chemical compound of metal, non-metal. Chemical polymers are chemical compound of non-metallic material, especially carbon and hydrogen. So here we are talking about the chemical composition. Now let us discuss the difference between these four types of materials: metal, ceramic, polymers, and composites, in terms of the properties. The difference between them, not in terms of the chemical composition, but in terms of the material properties. Especially the physical property like the density. The density, which is related to the weight. As you do have a dense material or a material with a high density, it means that this is a higher weight material, heavy material, right? Metals in general, they cover this group of material, because if you're gonna look even to the periodic table, most of the periodic table is metallic elements, right? And you're gonna have few non-metallic elements, or the number of the metallic elements, it is higher than the number of the non-metallic elements. So that's why metals, it is very common. Most, you could say that over 90% of the engineering application or the use of materials in different engineering application, we depend mainly on metals. Ceramics, we are using them, yes, there is some use of polymers, but metals, it is the most used material because they are covering lots of properties. Like for example, the density, there is a wide spectrum of in terms of the density. We start from 1 gram per centimeter cube up to like 30 gram per centimeter cube. Like for example, the magnesium, this is the material with the lowest or the smallest density. This is very light material, the magnesium. Aluminum, it is very light material as well. Titanium, the heaviest material ever is the platinum. This is very heavy material with very high density. So as you can see, the metal, they cover a very wide spectrum in terms of the density. They start from very light material to very heavy material. But ceramics, they kind of heavy material. Their density is kind of high. But they are not covering a wide spectrum like the case of metals, right? Polymers, they kind of light materials. Most of the rubber materials, most of the plastics, if you're gonna compare them to metals like steel or iron or whatever, they are very light in comparison to the metallic material. Here we are talking about the composite material, especially the composite material that contains polymers. We said that the composite, we can mix polymer with metal. Metal, it has good things, that they do have a high stiffness, they have high ductility, but they are heavy in terms of weight. Polymers they have a good thing. The good thing that they are very light in terms of weight. They have very low density. But in the meanwhile, they are very weak in terms of strength, in terms of mechanical strength. They are very weak material. But if we mix them through a composite material like metal polymer material, so we're gonna end up with A composite material that is strong as the metal but light as the polymer material. This is the good thing of the composite material. This is man-made material. This is what we are making. So as you can see, the composite here, its weight almost the same. Even it would be lighter than the polymer, because we could include some polymeric material like wood, for example, right? So we can end up with a very light material as a composite material, but in the meanwhile, it's going to be strong. So this figure compares the metal, ceramic, polymer, and composite in terms of the stiffness. And the next figure compares in terms of the strength. So what does it mean, stiffness of the material? Just to explain to you what does it mean, stiffness, let us consider that you do have two spherical balls, like soccer ball, and you do have another ball that is, this one is made of metal, and assume that this one is made of plastic, for example. So if I ask you to press on this ball with some kind of force by your hand, so this ball is going to be squeezed. It means that it's going to be deformed. It can be easily deformed, right? The shape is going to change easy. But if I ask you to do the same over the metal one, you couldn't able to deform or change the shape, right? So it's going to stick to the same shape. So we're going to say that this is very rigid in comparison to this one is going to be very elastic. Very elastic, it means that it is very flexible. It can be easily deformed. So the stiffness of this material is very low, but this material is very high in terms of stiffness. Why? Because it is rigid in comparison to the other one. So this is the physical meaning. What does it mean, stiff material? Stiff, it means a rigid material. So how, if the stiffness is high, it means that you do have a very stiff material. It is hard to change the shape of this material. Elastic material is a material that is flexible, that can be easily deformed. This is a material with a lower stiffness, like the case of polymers. If I give you a rubber material and I ask you to bend it and change its shape, you can easily do it by hand, right? All plastic material can be easily done. So that's why the stiffness of polymers is low in comparison to the ceramics, metals, or even composites. So this is the good thing of composite, that we mixing polymer, if we mix polymer with ceramic or metal, so we're gonna attain almost the same stiffness as metal and ceramic, but in the meanwhile, we're gonna attain, or we're gonna keep lightweight like polymers. So we are getting the good thing of polymer and the good thing of the ceramic. That's why composite material are heavily used in aircraft industry, for example, in aerospace application and aircrafts. All the components, the body of the aircraft is made of composite material. Why? Because we need to achieve a strong material, high stiff material. In the meanwhile, it is light, because the weight, it is a big deal if we're gonna talk about aerospace application, right? The aircraft, it should be light in terms of weight. That's why composite material are intensively used there. Also in terms of strengths, as you can see, composites, they do have almost the same strengths like metals and ceramics, but polymers, they kind of weak in comparison to the other types of material. Something that you should observe here, one would think that ceramic isn't strong as metals. No, in general, ceramics are strong and even stronger than metals. But why there is strength here in this figure, it seems that there is strength lower than the metal. Why? Because this type of strength, because we have different forms of strength, or different measures, or different parameters based on which we can measure how strong is a material. We can measure based on the tensile strength. The tensile strength, yes, metals, they do have ability to support tensile forces higher than the ability of ceramics to support tensile forces. The main reason behind this is that metals are ductile material, but ceramic are more brittle material. So what does it mean ductile? What does it mean brittle? These keywords will be explained as we move on in the course. Make sense? But very quick, ductile material like metals, they are very flexible. They can be easily bended without fracture. Like if I give you, for example, a stick or a wire of aluminum or a copper, like electrical wire that is made of copper. Copper it is metal material, and I ask you to bend it. It can be easily bended. It won't gonna be fractured, right? Even you can just twist it. But for the ceramic like glass, if you do have a piece of glass and I ask you to bend it, do you think that it's going to bend without fraction? No. It's going to be, if you try to do so, it will be automatically fractured. It means that ceramic is a brittle material. So ceramic is generally brittle. And metal is generally ductile material. Can be easily deformed. It is hard to deform. Hard to deform, it means that if you try to do so, it will be fractured. It means that it is brittle material, like fragile material, and ductile, it means it is flexible, kind of flexible material. So any ductile material, it has ability to support tensile forces higher than the ability of any brittle material. So that's why you're gonna see that the metal, it is higher in terms of strength, a little bit, especially tensile strength, than ceramic. But in the compression, the ceramic can support way higher forces under compression than metal. So generally speaking, ceramic in general, they are stronger than metals, especially under compression forces. Make sense? So this is something that you should understand, that is going to be clear again as we move on in the course. But polymers are very weak material in comparison to these groups. Composites, if we mix ceramic or metal with polymer, we're gonna end up with a strong material. In the meanwhile, it is light, as we mentioned before. Here, this is a comparison between these different types of material in terms of the resistance to fracture. Resistance to fracture, just to understand what does it mean this, assume that you do have a piece or a plate like this one, and this plate, it is made of metal. And you are handling a hammer, and I ask you to hammer over this plate. Do you think there is going to fracture? No, even if you heated the material, it's going to just, the hammer is going to put a mark over the table, but the plate, or the metallic plate, but the metallic plate will not be fractured. So we're going to say that the ability of this metallic plate to withstand the impact force that comes from hammering over the metal is high. So we're gonna say that it has high resistance to fracture. Make sense? If we did so the same with another plate, but the other plate is made of glass. Remember that glass is a ceramic material. This is metallic material. So that's why the resistance to fracture of the metal is very high in comparison to the ceramic, which would be made of glass. If you do have this one is made of glass, and you are using the same hammer, and you are applying the same hammering force, if you just one punch over the glass plate, it will be completely fractured, right? So we're gonna say that it has almost zero resistance to fraction. It cannot withstand any hammering or any impact force due to hammering over the plate. Right? So that's why the ceramic, they do have very low resistance to fraction in comparison to the metal. The main reason is that metal are ductile. As long as the material is ductile, it can absorb the impact force. Ceramics are brittle. So because ceramics are brittle material like glass, so they can easily fracture. So that's why they are weak in terms of resistance to fraction. Make sense? But polymer, how about polymer? Polymer, they do have low resistance to fracture, but this one, despite polymers, by the way, they are ductile. Even they are more ductile than metal, but they are weak in terms of resistance to fracture because their strength originally is weak. So their weakness in terms of supporting impact forces comes because they are originally weak. They are weak material in terms of its strength. So that's why also the resistance to fracture for polymers, it is low in as long as the ceramic, lower than the metal. Composites, since we are mixing, if we added a composite that include one of the metals, we are enhancing the fracturability or the resistance to fracture of this composite material to be kind of compared to the metal, but in the meanwhile it is light like polymer materials. Make sense? Also, this figure shows a comparison between metal, ceramics, and polymer and like kind of composite. But here we are giving it a name as semiconductors, which one type of the material that works like the same concept of a composite material. Metals in general, they are very excellent in terms of electrical and even thermal conductivity. They are good electrical conductors. So that's why all the electrical wires, they are either made of aluminum or made of copper, right? These are the most common types of metallic material that would be used for making electrical wires. Why? Because metals in general are excellent electrical conductors. But ceramics are insulators. Their electrical conductivity is very small, like polymers. Like for example, if you don't have any electrical wire, it should be covered by plastic, by a polymer material. Why? To be insulator, to save you from the electrical shock. If you just touch by bare hand, the bare wire, right? Electrical wire. So that's why polymer ceramics, they are good insulators in terms of electrical insulators. Ceramics, they are even excellent thermal insulators, but polymer, they are very weak in terms of thermal conductivity. Why? They cannot be used as thermal insulator because polymers, it is plastic, so it can be easily burned, right? Semiconductor, this is like a intermediate group of material that they do have a good conductivity and good insulation like the ceramic material. So this like kind of mixture between metals and ceramic. They are having intermediate concept between the excellent electrical conductivity and the very low electrical insulation or the very high electrical insulation. So this like semiconductor, they are not 100% conductors. In the meanwhile, they are not 100% insulators. Okay, so this works like the same concept of the composite material. This is for the semiconductors. So this table gives like a summary of the classification of the metallic, ceramic, polymers, and composites based on their properties. Like for example, like metals, here we are comparing properties like stiffness, as we said that the stiffness, how the material, it can be easily deformed or not. Like elastic or rigid. If the stiffness is high, it means that it is elastic, it is rigid, like metals, ceramics. But polymers, their stiffness is very low. Composite, it is kind of high, like metals. So in terms of stiffness, strength, density, ductility, electrical conductivity, heat conductivity, light transmittance, magnetic properties, chemical reaction, all right, or reactivity. So for example, the metals, they are excellent in everything except the light transmittance. They cannot transmit light. They are not transparent to light, but they are excellent in everything. They do have very good stiffness in many of the cases. They are good in terms of strength, good in terms of, they do have high density. They are ductile materials, relatively high electrical conductivity, excellent electrical conductors, excellent heat conductors. They are excellent in terms of magnetic properties. They also are excellent in terms of chemical reactions. So they are excellent in terms of magnets. They can be easily attracted to magnets. They are excellent in terms of chemical reactions. But ceramics, they are good in terms of stiffness, good in terms of strength. In many cases, as I said, ceramics are stronger than metals, especially under compression forces. They do have almost the same density like the metals, but they are brittle. Brittle, it means that they can be easily fractured. To remember brittle, remember the glass directly. They are insulators in terms of heat and electricity. They cannot transmit light. They are good in terms of magnetic properties and chemical reaction. Polymers, they are their stiffness, strength, density are relatively low. Their ductility is extremely high. This is the most ductile material ever. It should be polymer. They are excellent electrical insulator. Heat conductivity, they are not recommended to be used for any heat application because some of the types of polymers, and this is what we are going to discuss later in this course, they are changing properties up on heating. Some of them, they are totally damaged by heating. So they are not recommended at all in any thermal applications. This is for polymer material. Some of them are softened or decompose upon heating. In terms of light, they cannot transmit light. They are non-magnetic. They cannot be attracted to magnets. Their chemical reaction almost zero. They are not, unreactive in terms of chemical action. For example, these ceramics and metals, they are highly chemical reactive, especially for the oxygen that found in the air, the environment, in the atmosphere. Like oxygen can be easily do chemical reaction with metal, and this what result in oxide layers over either these ceramics or the metallic. But polymers, they are unreactive to this oxygen in the environment. Composite, they are mixing the good thing of these material. They are good and high in terms of stiffness, strength. The density is low as the polymers. They are ductile as the polymers. They are insulators, good insulators for heat, and they are good thermal and heat conductivity. They cannot transmit light. They are good in terms of my bad. All of these ceramics, polymers, composite, they can transmit light. Okay, but the metal, they cannot transmit light. It means that the light can go through the ceramic, through polymer. Like for example, light, it can go through glass, right? But it cannot go through metal part. So they can transmit light. Some of the polymers, they can transmit light. The same thing for composite. They are good in terms of magnetic properties and chemical reactivity. This is in terms of the composite material. Make sense? So this is the classification and the different types and even the properties of the material and their classification as metal, ceramic, polymer and composite that mainly depend on their chemical composition. The other thing here, and this is the last thing that we are going to discuss here, is the classification of the material but based on the material structure. So we can do this classification in general into two groups, either materials with microstructure or materials without microstructure. Materials with microstructure, like this group of material, that the material should have a microstructure. As we mentioned before, we discussed 4 different levels and types of material structure. We do have microstructure, we do have the microstructure, we do have nanostructure, right? So here we are talking about the microstructure. It means that the material, if we're gonna look at it through the microscope, we're gonna see that this material is a composition of different blocks that form of the micro scale that form the material microstructure, right? Like grains, at the case of polycrystalline material. Polycrystalline material is a typical example of a material with a microstructure. Why? Because polycrystalline material, the word poly, it means multiple. Crystalline, it means that this material is composed of multiple crystals. And each one of these crystals is a single unit inside the material microstructure. You're gonna see it if you're gonna look at it through the microscope. Typically the same, like this material example that we presented before over the previous video. Like this is one grain. This grain, it is a crystal. So this is a typical example of a polycrystalline material. Like if you're gonna look at it through the microscope, you're gonna see one grain which is like one crystal, and there is another grain which is a crystal or grain, they are the same. So this is another crystal, another crystal, another crystal, or another grain. So you have multiple grains or multiple crystals or polycrystals or polycrystalline material. So this is a typical example of a polycrystalline material. Remember that the word poly, it stands for multiple, right? So this is a typical example of a material with a microstructure. What is the building unit of a polycrystalline material? Is the grain or the crystal itself. Single crystalline material, you may have a material that is single crystal. The whole material is just one single grain. This is the entire material. There is no multiple grains, but still this material could be considered as a material with microstructure. Why? Because the atomic structure of the crystalline material, it is composed of multiple unit cells. So the main building unit in this case, or the microstructure of the material, depends on multiple unit cells. You're gonna find one unit cell, another one, another one, another one to form one single crystal. So the main microstructure depends on a building unit, which is a unit cell for the case of a single crystalline material. Also, it could be considered as material with microstructure. So this basic examples like the crystal would be covalent crystal, molecular crystal, framework, or ionic crystal, for example. But most of the metallic crystal, they are recommended to be considered as material without microstructure. But anyway, porous materials also. Porous, it comes from the, like the material, it has pores, internal voids. Like the material, it is like a structure, and there is like empty spaces between the structure inside the material, empty or voids or cavities inside the material microstructure, but these voids are very tiny, very small in the micro scale. So you're gonna have micro voids, micro pores inside the material microstructure. So that's why we're gonna give it a name as porous material. This could be considered as a microstructure, and in this case, the micropore, it would be considered the main building unit of this microstructure. Composite material also could be considered as a material with microstructure. Why? Because a composite material, one of the types of composite material that we may build the composite material that is made of polymers, and we're gonna embed inside these polymers some particles, like spherical particles. These particles would be in the micro scale, so we're gonna end up with a particulate composite material, or a composite material with particles made of ceramic or metal to give strength to this composite material. So these particles will form a microstructure of the material. So we could consider that composite material is one type of material with microstructure. So again, we are doing here the classification based on the microstructure. If we're gonna look to the material inside the microstructure, how it's gonna look like, does it has some, you know, like some microstructure or building unit or not? In case that it has no building unit or has no microstructure, so we're gonna say that this is a material without microstructure, like amorphous material. Amorphous material, it is a material with no specific building unit. Typical example of this is the most of the ceramic material like glass and most of polymers. Polymers, for example, they don't have a crystal structure. If you're gonna look at it through the micro scale, through the microstructure over a microscope to the microstructure of a polymer material, you're gonna find that this polymer material is composed of a chain of atoms, multiple atoms, lots of atoms, and these atoms form like a chain, and this chain is very kinky and wrapped together and very random. So you're gonna find a specific arrangement to these atoms, so you're gonna find a specific crystal structure to the material. The crystal, the key idea of the crystal, that atoms should be well arranged to form a crystal, and this is gonna be clear when we discuss chapter 3. But for now, amorphous material, a typical example like polymer material, glass material, many of these ceramic material, they are amorphous material, so they don't have a specific microstructure. Their microstructure, if you're gonna look at it through the microscope, you're gonna find it very random. The atoms are randomly distributed inside the material microstructure, so there is no specific building unit, so it can be classified as a material without microstructure. Some of the single crystalline materials also could be considered as material without microstructure, like monoatomic crystals and metallic crystals in general could be considered or classified into this group, some of them. So this is again classification, but based on the microstructure of the material. Now let us discuss, and this is the last topic, the advanced materials. Advanced materials, as I mentioned, these are newly developed materials that we are developing them based on our understanding of the relation between the material structure and the properties. So the key idea here that we found that if we could able to tailor the microstructure of the material, we would enhance some of the chemical, mechanical, and physical properties of a material. And this would result in new form of a material. This would allow us to develop new materials as advanced material that we currently developed in the field of material science and in the field of engineering science in general. Advanced materials are materials with exceptional properties. Their properties are exceptional, new. We didn't experience these properties and behaviors before by the natural material, which in many cases exceeds the natural material like metal, ceramics, and composites. We do have metal, ceramics, polymers, and composites, which are the man-made materials, right? So these materials, they do have specific properties. Now we can make materials with new properties that we didn't experience in any one of these natural materials before. Example of these are semiconductors, biomaterials, nanomaterials, and metamaterials. So these are the different types of advanced material that we are going to discuss. The semiconductor, as we mentioned before, they do have like intermediate properties, electrical properties between the fully conductors like metals and fully insulators like ceramics and polymers. So they have electrical properties that are intermediate between electrical conductors like mirrors and insulators like ceramics and polymers. Typical application to these semiconductors, we are currently using them in making amplifiers or in integrated circuit in general, like amplifiers. Biomaterials is another group of currently developed, and there is lots of research is done over the biomaterials. Biomaterials, simply they are biocompatible materials that they do not produce toxic substances and compatible with body tissues like our human being body tissues. We can use these biomaterials. And there are lots of applications and there are lots of fields actually. Even in some universities, they do have as a measure of biocompatibility, like we do have a measure of chemical engineering or a measure of mechanical engineering or even a measure of material science. We may have a measure of biomaterials, right? Or it could be at least a minor in some of the programs offered by some universities in the universe, like in the United States, in Europe, in different countries. So biomaterials, again, are biocompatible. Materials. A biocompatible material, it means that when we are using them in some biological tissues, like the tissues of our human being body or the animals or whatever, they do not produce any toxic materials. So we're gonna say that these are biocompatible materials or kind of biomaterials. Also, biomaterial could be considered this type of material that can be produced by some biomedical or biological interactions or biological reactions. Like we can produce them by using biological things. So this could be considered as also biomaterials. If we're going to talk about the engineering material that we are considering, like metal, ceramics, polymers, some of them are biomaterials, can be considered as biomaterial because we can involve them in some biological applications or some bio application. So generally speaking, we can say that metal, ceramic, polymers, and composites, they could be considered biomaterials as long as they are biocompatible. So some of the metals, some of the ceramics, some of the polymer material, they are biocompatible, so that's why we can group them into the biomaterial. A typical example is the titanium, pure titanium. The pure titanium is very excellent in terms of biocompatibility. So that's why most of the medical implants that require a strong material, because metal, as we discussed, it is kind of a strong material. So many of the medical implants that require a strong material mainly depend on pure titanium. But as I mentioned, having a pure titanium, it is kind of weak, but in some other applications, we would require more stronger titanium. So we could enhance the strength of the titanium by either alloying or using nanocrystalline material. This is one of the approaches that currently used for providing highly pure titanium and highly biocompatible. In the meanwhile, it is ultra strong, very strong titanium that would be used even for locking compression plates. These plates are used as implants for the tibia or the femur to fracture tibia or femur. So we can use this pure titanium in such application, and that's why pure titanium could be classified as biomaterial because of its high biocompatibility, right? we can implant this material inside the human being body, and it can live inside the body for years and nothing wrong. There is no toxic material, there is nothing, so it is high biocompatible material. Nanomaterials. So we discussed semiconductors, biomaterials. Now let us move to nanomaterials. Nanomaterials, actually, this is also newly developed group or class of material with exceptional properties. And now we are involving these nanomaterials in so many applications, and we are considering and expecting a lot more to be done over these nanomaterials, especially in the application side, and involving them in different applications, as I mentioned. Nanomaterials are materials with characteristic dimension with 100 nanometer, or a building unit with sizes lower than 100 nanometers. So what does it mean? Generally speaking, we would have a nanomaterial that the material would be in the conventional size, like the material like this pen, for example. So it is just the conventional. It is not nano, right? I can see it. Nano is something that you cannot see by the naked eye. You should look at it through a microscope, a special microscope, to zoom in so you can increase the size, so you can see a nanoscale. Nanoscale, as we mentioned, it is 10 to the power -9. So it is very tiny thing. So we would have a nanomaterial, and the nanomaterial, it is in the microscopic scale, in centimeter size, for example. But how could this one is a nanomaterial? This would be a nanomaterial in case that its microstructure, the thing that inside the material, it is nano. So this could be classified as a nanomaterial. Like, for example, if we're gonna consider the typical example of a polycrystalline material, this microstructure. We said that this is a polycrystalline material. Why? It consists of multiple grains, one grain, another grain, and so on. What is the size of this grain? It is 20, almost 20 micrometer average size, or 15 micrometer, or 10 micrometer average size of all of these grains, right? None of these grains is in the nanoscale. None of these grains is less than or equal 100 nanometer. All of them either 10 micrometer or above. Make sense? So we're gonna say that this is a microstructure. This is not a nanostructure. But if we use the technology, one of the manufacturing methods that we could refine it means decrease the size of these grains to be in nanoscale. Like, we're gonna refine all of these grains and decrease their size to be all of them less than 100 nanometer or equal. So in this case, we are turning and changing this microstructure to be nanostructure. If we did so, we're gonna end up with a nanomaterial. We are turning the material from being conventional material, conventional polycrystalline material, to be a nanocrystalline material, to be a nanomaterial. If we did so, we are enhancing the properties of the material so much. So this is the key idea of a nano. This is one type of a nanomaterial, but this nanomaterial, it would be in the conventional scale, in the conventional form, like this pen, but its microstructure, in this case, it converted to be nanostructure. It has a nanostructure instead of having microstructure. We refined what's inside the material. We made what's inside the material to be nanoscale, to be nanostructure. So that's why we do have the name as nanomaterial. So this is one group of a nanomaterial. This group of nanomaterials is known as nanostructured material. Like the material, it is contained, or the material, it consists of nano building unit, not micro, nano structure. So it is classified as nanostructured material. This is one group of the nanomaterial. There is another way of making a nanomaterial that we can squeeze the size of this pen to be nanoscale. Like, assume that we're gonna manufacture typically the same pen, but it will be manufactured in the nanoscale, very nano thing that you cannot see by the naked eye, but if you zoom in, you're gonna see pen. So this is nano-sized material. Like the entire material, it has been sized. It has been squeezed in terms of size to be nano-sized. So this is a form, another form, or another way of developing or making a nanomaterial as nano-sized material. So generally speaking, we can classify materials into either a material with a characteristic dimension, which is lower than 100 nanometer as nano-sized material, or with a building unit whose size is lower than 100 nanometer as nanostructural material. So we do have nanostructural material or nanosized material. Nanostructural material like nanocrystalline materials. Nanocrystalline material, this is polycrystalline material, but the grain size, it became nano instead of being micro. The conventional thing, if we bring a polycrystalline material by nature, it will be in the micro scale. The grain size will be in micro. But using our technologies, we can refine this grain, this micro grain, to be nano grain. So in this case, we're going to end up with a nanocrystalline material. This is with a better property than the conventional polycrystalline material. Nanoporous material, we do have porous material. But we may, porous material, we mentioned before that the porous material is a material with pores inside it. But the size of the pore of the conventional porous material, it is usually in the micro scale. Now we can do nanoporous material. Nanoporous, it means that we can design this pore to be in the nano scale. So we're gonna end up with nanoporous material that use currently in different applications and have better properties over the conventional porous material. Nanocomposites, we do have composite material, right? Which its particles inside the material microstructure would be in the micro scale with a microstructure, but now we can do and manufacture a nanocomposite whose microstructure turns to be nanostructure. So it became with a nanostructure instead of being with microstructure. So these are common types of materials with nanostructure, materials with nanosize like carbon nanotubes, like graphene sheets, like nanocrystal. We may have a material with a single crystal, but the size of this crystal is nanoscale. So, for example, if we're gonna discuss the nanocrystalline material, nanoporous and nanocomposite, these are the three types of nanostructural material, the first group. Nanocrystalline, as we mentioned, are polycrystalline material that composed of multiple grains, but the grain size, it's gonna be nanograin instead of being micrograin. So nanograins, with nanograins and the grain average size, it should be lower than 100 nanometer. What we found up on making this nanocrystalline material, when we refined and decreased the size of the grain inside the polycrystalline material and we produced a nanocrystalline, we found that the strength of the material is highly enhanced. Like we are obtaining over 300% enhancement or increase in the strength. So the material became 300% stronger than the conventional polycrystalline. Like if you're gonna make nanocrystalline material, it is 300% stronger than the conventional polycrystalline material. But in the meanwhile is that the brittleness or the material become more brittle, that the ductility of the material intensively decrease, and this is one of the challenging of producing nanocrystalline material. So people these days are interested in finding a way of enhancing both the ductility and the strength of the material. But what we found actually, upon increasing the strength, we found that the ductility decreases and we're gonna end up with a brittle, and this is one of the challenges that we try to fix as material scientists. Nanoporous materials are materials with high fraction of nanovoids. They are very light but very strong in the meanwhile. Nanocomposites are composite materials reinforced by nanoparticles. Instead of using particles in the micro scale, we're gonna have nanoparticles, nanofibers or nanorods or tubes. Like we could make a composite material from a carbon nanotube, for example. So we're gonna end up with a stronger material than the conventional composite because of the enhanced adhesion. So what we have in one of the essential mechanisms of increasing the strength, like the bonding, or the not bonding as a chemical bonding, it is adhesion between the particles inside the material and the matrix material, the exterior of the material. This adhesion and this bonding is enhanced upon decreasing the size of the nanoparticles. So we are increasing the contact area, and this would give better properties and would eliminate many of the defects and problems of the conventional composite material upon using nanocomposite. And there is a growing interest these days, and China are doing very good in this field of in terms of research and in terms of development and using this nano-composite material. The second group of material, as I mentioned, this is the nano size, that the entire material size is going to be in nanoscale. Like the case of nanocrystal, like we could form a nanocrystal, and like the material is just going to be a single crystal, and the size of this crystal is going to be nanoscale. Like these two figures here, or images of mechanical resonators, like these like beams used for some medical application or some different applications. So nanocrystals are nano-sized materials made of a single crystal. As I said, this just one single crystal, but it is nano-sized. Example of these are single crystalline diamond and single crystalline silicon. Like you're gonna have the entire material just gonna be one single crystal of silicon, but we're gonna shape this single crystal into nano thing. The same thing, it would be made of diamond. These are the most common two types, used types of material in this application. The properties of these materials are very strong materials with very high quality factors. These quality factors are very important. This quality factor is very important to enhance the measurability of the frequencies using these mechanical resonators. So I won't gonna go deeply through what does it mean quality factors, so you're gonna be confused. But anyway, it gives very strong material, very high quality factor, which make them very potential to be used for MEMS and NEMS. MEMS, which is micro electromechanical devices. These electromechanical devices are in the micro scale, or nano electromechanical devices that the entire device is going to be in the nanoscale. So we are using them as sensors that will be used for very advanced application. Like for example, in this figure, if you can observe the scale bar here, it is 1 micrometer. It means that, for example, the entire length of this beam is going to be like around 100 micrometer or something. The thickness is going to be in nanometer. So this resonator, this work has been published in 2004 by a group of scientists that they use this resonator, they manufacture this one of a single crystal of silicon. They did it by some chemical method to manufacture this beam, and they use it to, and they drop here, this small circle here or sphere thing, it is vaccina virus. It is one single particle of a virus. And they use this resonator to measure the mass of this, or the weight of this virus particle using this resonator. Make sense? So this mass, it is very important in the design of the vaccine for this virus particle, or it would be even for the development of the treatment of the medicine that would be used, or the vaccine for this virus, right? So based on their measurements, the medical scientists, they could able to drive and develop some vaccines for this virus. The same thing here, this would be used for this diamond cantilever. This is made of diamond, and as you can see, the thickness of this one, it is 100 nanometer thickness, and the thickness of this thickness here, it is 5 micrometer, but the thickness of the this small thing, it is 100 nanometer. So it is nanoscale thing, and also it is used for some resonator application that used for the electromechanical systems as nanoscales. So this is nanocrystals. We could make also carbon nanotube. Carbon nanotube is one of the most common type of nano-sized materials as nanomaterial. They are carbon atoms arranged in a tubular shape. Like we manufacture this thing, this carbon nanotube, by chemical method. We could we mainly use chemical method to produce this carbon nanotube, that we are arranging carbon atoms together, and we form this carbon sheet of carbon atoms in a tubular form to give us a carbon nanotube. And we are using them in different applications. They are ultra strong material. They do have very excellent quality factors. They are used in many applications like making nano-composite, MEMS and NEMS, and so many other applications. For example, like in this figure, this is a very thin carbon nanotube. If you can observe, there should be here a carbon nanotube, And these scientists in 2012, they could able to drop a single atom over this carbon nanotube. Then they use this carbon nanotube to measure the weight of this single atom. So it was a very huge achievement in the field, and as they could able to produce this carbon nanotube and use it for the measurement of this single atom. It was a great achievement at that time in 2012 that they could able to make this carbon nanotube as a bridge in this way. This is different forms of multiple carbon nanotubes that already, even now we can make the carbon nanotube to be in the micro scale, but generally we can make them in the nanoscale. Also, graphene sheets, they are carbon atom but arranged over planar sheets. So simply the carbon nanotube, just to understand the carbon nanotube, if we could able, as shown here, this is carbon atom, this is another carbon atom, and so on, to form like a unit cell, and then you're gonna repeat these carbon atoms in over a sheet. So this is gonna give us a graphene sheet. If we make this sheet in a tubular form, if we just turn this one to be tube, so we're gonna end up with a carbon nanotube. This is, and by the way, we are doing all of this by using chemical methods. We are not using mechanical approaches to produce these things. But for example, for the nanocrystal material, we are using mechanical methods. So mechanical method of processing, here we are talking about material processing, if you remember. It means that to produce a nanocrystal material, you have to use a mechanical method of processing nanocrystal material. The same thing, nanoporous, we could use a mechanical method or a chemical method. Nanocomposite, we could use a chemical method or a mechanical method or a chemical, but many of the cases we are using mechanical method. But here we are using chemical method. Here for carbon nanotubes and graphene sheet, we mainly using a chemical approach to method to manufacture. So this is chemical method of material processing to process or produce these graphene sheets. Graphene sheets are a strong material used for many applications like nanocomposite MEMS and NEMS. Even currently, we are trying to use these graphene sheets for water desalination application. Like this is the seawater that include the lots of salts and ions. And we are using a special graphene sheet to purify this water. So we're gonna end up with drinking water as output of this graphene sheet that would be used for water desalination application. And there is a growing interest in this field, especially in the mechanical engineers, to develop and doing research over the use of the graphene for water desalination. The last thing here is metamaterials. Metamaterial, this is a newly developed material that first it had been developed to be used for optical application and physical application. Now we are doing as mechanical engineer, we do have an interest to involve these metamaterials for mechanical application. So the good thing of metamaterial and what makes them different than nanomaterial. Nanomaterial, the key idea of a nanomaterial, as I mentioned, that it depends on the design, especially the design of the material microstructure, to provide some exceptional properties that we haven't experienced before in the conventional material. But metamaterials, as for metamaterial, they are newly developed material with exceptional properties, but anomalous, weird, strange properties. Strange thing that we didn't experience. Even so many people didn't believe this thing till the moment, right? So what we basically do for this metamaterial. So again, metamaterials are newly developed material with exceptional and anomalous properties. Examples of metamaterials with anomalous properties are materials with negative Poisson's ratio, commonly known as exotic materials. What is a negative Poisson's ratio? To understand this, for example, as you can see, this guy, he's using this like rubbery material, and he's trying to press over this material from these two ends. If this material is a conventional material, like assume that you have a material like this way, and you're applying some forces over the material here. So as you compress the material, what should be happening to the width, to this dimension? This dimension, it should be increasing, right? Like if you squeeze the material, intuitively the material will be shortened. And in the meanwhile, this dimension, it should be increasing. So we're gonna say that this material has a positive, its Poisson's ratio is positive Poisson's ratio. It means that if you try to squeeze the material, it will be stretched from the lateral direction. But this is not happening for this material. If we try to push the material from these two ends, and instead of this material, it should be like barreled. It should have a barrel shape in this way. No, this is not happening. And instead, the material is contracted, compressed from the middle. This indicates a negative Poisson's ratio. So it is weird thing. This is not conventional. In the conventional material, metals, polymer, ceramic, even composite materials, all the Poisson's ratio should be positive between 0 and 0.5. We didn't experience before any material with a negative Poisson's ratio. But with these metamaterials, we can achieve a negative Poisson's ratio, and this is a great achievement in the field of material science. We understood this based on our understanding of the material structure and how it would impact the mechanical properties of the material. Like the concept of the metamaterial is to specially design the material microstructure or the material structure to achieve this weird behavior, to achieve this anomalous behavior of the material, like negative Poisson's ratio, like negative stiffness. We usually like equivalent negative stiffness. Any material in general, it should have a positive stiffness. Now we can achieve a material that behaves like it has a negative stiffness. We can produce or make a metamaterial that behaves like it has a negative thermal conductivity. We knew that the thermal conductivity of any material should be positive value. Now we can make a material that its behavior seems like it has a negative thermal conductivity, even a negative mass. Do you think that any material that would have a negative mass, like negative 10 kilograms? No. Any material should have a positive value of mass, positive density, right? The density like 10 kilograms, 5 kilograms, and so on. But do you think that we can make a material, its mass to be negative, like negative 5 kilograms? So what does it mean, negative 5 kilograms? We can do this material but physically the material has a mass that is positive, but its behavior, it behaves like it has a negative mass. We can do this material using metamaterial, and we already developing this. So this is the basic concept of the metamaterial. Again, metamaterial are newly developed material with some exceptional and weird, anomalous properties that we didn't experience before in the conventional material, like negative Poisson's ratio, negative equivalent, negative stiffness, equivalent negative thermal conductivity, and equivalent negative mass. Make sense? So now I'm just gonna leave you with this video just to give you more details about the auxiliary metamaterials, which are materials with negative Poisson's ratio. And this type of material actually, this could be one of the ideas that you could consider as a project for this course. So let us just watch this video very quick, then we're gonna finish this class.
Today we will be discussing auxetic materials, but first let's talk about a regular material. When a normal material is under axial tension, it usually tends to compress in the lateral direction. In contrast, if the material is compressed, it usually tends to expand in the lateral direction. The applied force results in a change in length, which can be characterized by a longitudinal and lateral strain. The ratio of the magnitude of the resulting transverse and axial strains from the axial load is called Poisson's ratio. The shear modulus, denoted by G, of a material governs its plastic deformation, while the elastic modulus, denoted by E, governs its elastic deformation. As shown, the shear modulus is inversely proportional to the Poisson's ratio. As a result, Poisson's ratio governs the material's ability to recover elastically following an external stimuli. Auxetic materials are materials which exhibit a negative Poisson's ratio. As a result of their Poisson's ratio, they have an increasingly large shear modulus, which means indenting auxetic materials is increasingly difficult. But what does this mean for the material's response to external forces? As a result of their negative Poisson's ratio, auxetic materials experience lateral expansion under axial tension and lateral contraction under axial compression. This is the opposite of how a normal material responds. Auxetic materials exhibit negative Poisson's ratio as a result of their subunit structure, not as a result of their chemical composition. Common structures include the bow tie motif and chiral honeycomb. These structures can be assembled in 1D, 2D, 3D, or in fibers. Auxetic materials are manufactured using various nanofabrication methods, such as lithography-based ceramic manufacturing, direct laser writing, and DNA manipulation. The properties of the structure can be engineered to fit their desired application. Research on auxetic materials is increasing because, in theory, an auxetic material will never deform plastically. This means that it will never fail and will always undergo reversible deformation. This amazing property would provide lightweight materials with superior energy absorption and dampening. There are many applications for auxetic materials in fields such as biomedical, aerospace, building and construction, smart textiles, and defense. Research is being done for other fields and applications. In the biomedical field, devices such as artificial blood vessels are being tested. During a pulse of blood, the walls of the vessel will increase in thickness rather than decrease, which will greatly reduce the probability of rupture. Medical bandages that react to the swelling of a wound in order to produce a controlled release of an antibacterial agent are another possibility. The unique bending characteristic of auxetic materials, where a convex dome shape is created rather than a saddle shape, could also be useful for practical applications. One way they are being tested for implementation is in the conical frontal area of airplanes. Another airplane application is during cargo drops due to the increased energy absorption properties of auxetics. For use in the building and construction industry, negative Poisson's ratio materials are being implemented as the core material in sandwich panels. These panels are used in applications where high structural rigidity and low weight are required. Shown here is its use in an armored vehicle. Smart textiles made from auxetic fibers can be used to create crash helmets, body armor, and sports clothing with increased dent and fracture resistance as well as an increased energy absorption. To oppose these safety applications, a special bullet with an outer core made from auxetic materials is being researched that could increase bullet speed by decreasing lateral expansion of the bullet due to thrust and centripetal forces in the barrel of the gun. Other possible applications of materials displaying negative Poisson's ratio include fiber seals, press fit fasteners, gaskets, fillers for highway joints, strain sensors, shock and sound absorbers, air filters, and shoes.
Alright, so this is for these metamaterials, and as already explained in the video, there are lots of applications that we are developing this metamaterial these days for. So it is very hot topic these days, especially in these mechanical applications. So that's it for this chapter. This is chapter 1. The objective is just to give you introduction about these different keywords. We have introduced lots of keywords. I have spent enough time to explain these keywords with some more details, because this is very highly important, because as I mentioned, these keywords will be used a lot during the class, right? So that's it for this chapter, and these are the different learning outcomes that we already covered. I hope everything is clear, and if you do have any question, for sure you just feel free to ask during the class meeting, or even you can email me with your question, right? So thank you, and that's it for today, and see you in the next meeting. The next meeting we're gonna start a new chapter, which is chapter 2. Thank you.